Best PCB design and measurement practices. Let's get right to our topic for today. Today's webinar is really the first in a series that we're presenting in 2024. It's the series we're calling In the Lab with Eric Bogatin. That's me. And throughout this series, we're going to be introducing you to what I think are some of the most important best PCB design and measurement practices. This year, we're going to present 11 different webinars in this series. They're all going to focus on the same topic of best design, measurement, and analysis practices, but it's really going to focus on prototypes. And we'll interchange a little bit of prototypes in printed circuit boards and solderless breadboards, and you'll see why as we get further along. Most of these presentations that we're going to be doing are based on the printed circuit board design class that I've taught at University of Colorado in Boulder. It's also related to my textbook, and here's a copy of the cover page here. It's published by Artec, and it's really detailing a lot of the principles and the methodology that we're going to review in this webinar series. And so if you would like to get more details about this topic, I strongly encourage you to take a look at the textbook that's available from Artec. And you will have an opportunity to sign up for all 11 parts of this webinar series when you get the registration page for any one of them. Well, let's jump into the first topic of today. And today is kind of like an overview. It's, you know, if you go to the opera, at the very beginning, they play the overture. And the overture is a little snippet of all of the tunes that you're going to hear throughout the opera in all the different scenes. Well, that's kind of what today's webinar is. This is a little bit of an overview of some of the principles that we're going to be paying attention to. And I'm going to try to put in perspective the process of designing a circuit board when performance is important. We're going to talk a little about what does it mean to have interconnects when they're not transparent. How do you approach designing circuit boards in that case? And then I'm going to introduce you to what I think are some of the most important signal integrity and power integrity problems that you want to design out. Because after all, that's one of the most important design principles is you want to you want to identify the problems, design them out at the beginning. And in order to understand what the root cause of those problems are, there are also a couple of important signal integrity principles that I'm going to introduce today. And then we'll finish up with, okay, so what have we learned? Given the problems, given these principles, what does that tell us about how we want to both design the circuit boards to eliminate these problems and also, equally important, be able to measure these effects? And I'm going to just tease you a little bit with these answers because these questions are most of what the rest of this 11-part webinar series is about. Let's talk about interconnects first. Let's start out talking about the role of interconnects in design. The very first step in designing a circuit board is the schematic. The schematic is a representation of all of the parts that are going to be used, the components that are in the design, and how they're connected together. Each of the components have ends or terminals, and the wires show how those terminals are connected together. In a way, the schematic is a graphical representation of the database of the netlist. It has all the components, all their terminals, and which terminals are connected together. Only it's a graphical representation so we can see it all at once. When we turn that schematic into a layout, that is the physical implementation of all of those ideal wires and also the white space. These interconnects that we draw, the physical interconnects that represent the connections between the terminals, they live in that white space and in the wires of the schematic. If the electrical properties of these interconnects are transparent and they don't affect the signals, then when we design the circuit boards, it's all about all the other design for issues. It's about design for manufacturability, design for reliability, design for tests, design for assembly. Those are the factors that you have to worry about in designing the circuit board if the interconnects are transparent. It's not about the electrical properties of the interconnects. But unfortunately today, in almost every single design, interconnects are not transparent and we have to worry about their electrical effects. And that means that when you look at the impact interconnects are going to have on the performance of the system, what we see immediately is that the design in the interconnects can never improve the performance of what the ICs themselves are capable of. All they're going to do is screw things up. Once we use the interconnects to establish connectivity, and connectivity is correct, so we have an accurate representation of the database of the netlist. The only thing interconnects are going to do is screw up the performance. They are going to add noise and degrade the signals. And that means then that the goal in interconnect design, when the interconnects are not transparent, when their design influences performance, in other words, influences the noise that's generated, our goal in interconnect design is to minimize how much those interconnects screw things up at an acceptable cost and risk. And that is the number one most important guiding principle when we deal with interconnect design. And what do we mean by transparent? Well, if you have a design like this is a design that is based on solderless breadboards and a lot of discrete components and wires. If this design works, and I use that term works loosely, but whenever I use that term works, I always mean it meets some performance specification or requirement, some documentation that says these are the features and functions this product needs to demonstrate when it is turned on. If this circuit, as it's implemented, works and meets that performance spec, that means that the electrical properties of the interconnects, other than their ability to provide connectivity, their electrical properties are irrelevant. The interconnects are transparent. And that means that when you design the circuit board to replace the solderless breadboard, design of the interconnects for electrical performance is totally irrelevant. It doesn't affect any performance feature of the product. That means that it's the other design for terms that are important. Design for manufacturing, DFM, DFT, DFR, the cost, the supply chain management for all the components. That's what's important in the design. But for our series, we're going to be dealing with the case when interconnects are not transparent. That means how we implement the physical design of the interconnects influences the noise. And why is that? Why are interconnects sometimes not transparent? How do the interconnects, the physical implementation of the interconnects, how do they actually affect the electrical performance? How do they affect the signals? And unfortunately, it's all based on Maxwell's equations. That the signals that are generated by the devices, those are the voltages and currents in a simplified view, or magnetic fields and electric fields or electromagnetic fields, when they're created by the devices, they interact with the conductivity and dielectric properties of the conductors and the dielectrics. They represent electrical properties of the interconnects. They are boundary conditions in which the fields interact, and those fields, electromagnetic fields, are all governed by Maxwell's equations. And so it's how the properties of electromagnetic fields interact with the boundary conditions of the conductors and dielectrics and those material properties. That combination results in the other electromagnetic fields at receivers. It's the interactions of how those fields interact with the materials that give rise to the distortion that they can create. I say unfortunately because in order to understand how these interconnects are going to distort the signals, how they're going to introduce noise, unfortunately, we have to understand Maxwell's equations. And, you know, in general, when you get into the deep levels of engineering, all of engineering is about mathematical representation of the real world. It's about using ideal models because we can solve problems much more quickly in the ideal world than in the real world. That's where virtual prototypes come in. And all the properties, the electrical properties of interconnects, are all governed by Maxwell's equations. And if you haven't studied Maxwell's equations, then, you know, it kind of looks like this guy here. He says, but this is the simplified version for the general public. And that's why I think it is so important. If you're really serious about signal integrity, power integrity, there's no substitute for understanding Maxwell's equations. But if you haven't gotten there yet, and you're still moving up the learning curve, then I think there's things that we can do to help understand what these equations are telling us. And that is really the secret to design. You know, design is a creative process. It's about using your imagination and thinking of possibilities, speculating possibilities, and we fuel our intuition by the understanding of the electromagnetics of the interconnects. Now, if you don't have that good understanding of what the equations are telling us, then we can do a few other things to help kind of move up that learning curve. And that's where prototypes come in, virtual prototypes or real prototypes. As virtual prototypes, we build them in simulation tools, and those simulation tools which use Maxwell's equations in their engine and solve Maxwell's equations, they can help visualize for us how those fields are behaving and interacting with the interconnects. And that can help develop some intuition about what the equations are telling us. And we can do the same thing with real prototypes as long as we understand how to measure the noise that is generated that we care about. And that's what we're going to be doing in most of the lectures in this webinar series. We're going to be looking at visualizing those electromagnetic fields, understanding what they look like in different situations, how they're driven by Maxwell's equations, and we're going to look at how can we build some physical prototypes that illustrate some of these problems that can arise, the best design solutions to eliminate those problems, and pathological situations where those problems can arise, and how do we go about measuring those effects so that we can compare how does the physical design and decisions we make in the physical design affect that noise that's generated. And that's why this webinar series is based on best design practices and best measurement practices, because the measurements and the simulations will give us insight into what's going on as long as we interpret the results correctly. And that's what I'm going to be guiding you through in this webinar series. Well, it kind of begs the question then, okay, so what? Well, how are we going to deal with this? If we have a situation where interconnects are not transparent, how do we design the product? How do we take into account the impact the interconnects are going to have? And here's a really simplified design methodology when we have to worry about the interconnects not being transparent. Here's literally the process we're going to go through. We're going to first identify what are those problems, the signal and power integrity problems that can arise, because we're not the first ones to look at these problems. These kind of effects have been around for a long time, and I'm going to help identify for you what those problems are. The second is, the number one golden rule in solving a problem is, if you want to fix a problem, you have to know the root cause, and you fix the problem based on the root cause. And so once we've identified the problems that can arise, then we're going to want to identify the root cause. And of course, to understand the root cause, that's where the essential principles are so important. And based on those principles and the root cause, that will give us some guidance into developing those best design practices so we can reduce those problems, again, based on the root cause. And once we've implemented what we think are the best design practices, then we can evaluate how good a job have we done, how much noise is there, how much do we want to pay for that reduced noise, how important is that, balancing those trade-offs using virtual prototypes in the simulation environment or building some real prototypes that are designed to either accentuate the problem or reduce that problem, and again, measure the impact the interconnects can have. And that's how we're going to explore design space to balance those trade-offs. Ultimately, when I use that word performance, I really refer to the role interconnects play in terms of the noise that they're going to introduce, at what risk and at what cost. And as we apply this process, we're going to always encounter reference designs that are going to suggest, oh, you have to include this effect or that effect, or you have to have this feature or that feature. And whenever we look at changing or adding a particular feature in the interconnects, when it comes to how it affects performance, we always want to ask the question of, okay, if we're supposed to add some feature to improve performance, what is the problem that feature is addressing, and how is adding that feature going to solve that problem or reduce that problem? That is going to be one of the most important questions we keep asking of every design guideline that we implement or that someone tells us you should implement. What is the problem that it solves, and why does it solve that problem? And can we analyze the impact that solution has based on virtual or real prototypes? How are interconnects not transparent? What could possibly go wrong? Here's an example of some interconnects of a kind of a system here, a channel, the devices and the board and the connectors and daughter cards and other receivers over here. What can possibly go wrong? This is just one example of looking at one of the channels and the signals as they go from the transmitter all to the receiver. Clearly, that's a problem. And when you look at what causes this collapse of the eye as an example of a problem to avoid, when you look at what goes into this signal integrity problem and other signal integrity problems, it looks like there's just this huge long list. Here are just some examples of these, actually taken from a bunch of other webinars that we've presented here over the last few years. These are examples of some of the problems that can arise. How do you make sense of it? How do you put it in perspective? And so I'm going to offer you, as part of this series, a very simple perspective on thinking about all of the problems that interconnects can create and how do we go about fixing those problems methodically. Unfortunately, I'm going to make some generalizations. And when you make generalizations, you run into these two problems. And I always like to refer to this little statement here about Harvard students and MIT students. You can guess which one I am. Harvard students learn less and less about more and more and end up knowing nothing about everything. And MIT students learn more and more about less and less and end up knowing everything about nothing. These are the kind of the two extremes when we make generalizations. It's so broad that we don't know what to do with it, doesn't give us any information, or it's so narrowly focused that it applies to this one situation and nothing else. And so I like to use that phrase that sometimes an okay answer now is more important than a good answer late. And so I have to give some generalizations to put in perspective the problems and the solutions. And so I'm going to ask a little bit of indulgence. Whenever you come up with a generalization that is useful, there are always going to be exceptions to it. And so look at the forest first, and then you can look at some of the trees. And so the first generalization that I want to introduce you to is a simple model that I developed, and I published it in the textbook. You can get more details on it. But it's a way of mapping the kinds of problems and kinds of effects that arise in circuit boards because the interconnects are not transparent, because they introduce noise. It's a way of mapping those problems in terms of the rise time of the signals and the length of typical interconnects in the boards. Because that's kind of the scaling, that the longer the rise time, the less the impact, unless the interconnects are long. The longer they are, the longer the rise time is going to introduce a problem. And so in the textbook, I go through the model, but I'll just kind of walk you through the details here. If you have a long enough rise time, this is 10 nanoseconds, 100 nanoseconds, if it's in the tens of nanoseconds and lengths on the order of an inch or less. So if it is long rise time and short lengths, many cases, interconnects can be transparent. Yeah, you can find an extreme case where something that is 1 inch long and 1,000 nanoseconds rise time, there still could be some problems the interconnect introduces, especially if you have very high bit level ADCs or you have really high currents. You can find an exception, but generally, in most cases, if you're in this regime over here, rise times in the tens of nanoseconds, lengths very short, or long rise times but longer lengths. If you're in this region, interconnects are transparent. It's a who cares. You're designing for connectivity, you're designing for cost, you're designing for manufacturability. As we go to longer lengths for a fixed rise time, if we have a fixed rise time of 10 nanoseconds, for example, and we look at longer length interconnects, we get into the regime where the interconnects are no longer transparent, but we can think about them, we can model them in terms of lump circuit approximations. So we think about the interconnects in terms of their capacitance and inductance and resistance. In this regime, we find the first problem that breaks a circuit board, the first problem that is critically important is switching noise. And that means that anywhere above this range, anywhere over here, switching noise is going to be an important issue and you have to worry about it. And that's what we're going to be talking about in this webinar in particular. And so if we're in this regime, anywhere, switching noise is important. And then as we go to longer interconnects, we're talking about 10-inch long, 10 nanosecond, 10-inch long, that's when transmission line effects start to play a role. The transmission line properties of the interconnects are important, and the problems that arise in transmission line circuits are important. Things like reflection noise, about termination, about routing topologies, about crosstalk between uniform transmission lines. These are some of the features that depend on the transmission line properties, and if we don't engineer them correctly, those sources of noise can break the system. And then if we're talking about a short rise time and we talk about longer and longer interconnects, when we start talking about nanosecond edge and 100 inches long, then we still have all of these problems in those systems. And in addition, we also have the high-frequency properties of the interconnects, the problems that arise in high-speed serial links. This is about the losses in the interconnects. This is about differential pairs and skew and length matching and glass weave fiber effect. And this is about stubs, and it's about resonant coupling, all the problems that arise in high-speed serial link type systems. They still suffer from these same effects of reflection noise and termination and routing topology. They still suffer from the switching noise problems and additional ones. And so depending on what rise time your typical signals are and what interconnect lengths you're dealing with, you're going to have a board that's in a different regime. And every one that's in this regime, other than when interconnects are transparent, every one of the designs is going to potentially suffer from or be sensitive to switching noise. And that's why we're going to start our journey looking at switching noise, because all boards that are outside of this regime, that are not transparent, all boards are going to have switching noise problems. And what's switching noise? Switching noise arises from an inductance, an LDIDT. DIDT is the change in current. When current changes through an inductor or through a mutual inductance, that's when switching noise is generated. Switching noise is the noise that's generated when currents switch, when they change, and those changing currents are passing through, interacting with an inductance. So we have an inductor, we'll put a DIDT across it, we get a voltage across it. Constant current through that inductor, no voltage across the inductor. It's only when the current changes through the inductance that we get a voltage generated, and that voltage is the noise that we want to reduce. Here's just a really simple example, and we'll see a number of situations like this in upcoming webinars, and we'll see how to measure this, and we'll see how to engineer interconnects to accentuate it, that is pathological cases, and how to reduce it using best design practices. But here's an example of looking at an I/O on a microcontroller. We can see it switching here, and look at the noise that's generated on one of the lines from switching noise. Why do we call it switching noise? Because look, it only appears when the I/Os switch, when we get currents flowing from the edges changing. And so we call it switching noise because it only arises when those I/Os switch. This is one example of switching noise. Well, given this perspective of this kind of length bandwidth product and the mapping of what the rise time is and the interconnect lengths to tell you what kind of problems that you're going to encounter, well, then the next problem is looking at the complexity of the boards. And so we're adding another dimension here. So here in the horizontal axis, this is the length bandwidth product. This is where those problems arise. So at this end here, interconnects are transparent, rise time and lengths are short enough, long enough so that you don't have electrical properties of the interconnects don't affect the signals at all. Here's that regime where you get shorter rise times or longer lengths. Switching noise, the DIDTs through inductances are important. Here's where transmission lines are important. Here's where those extra high-speed serial link effects are important. And on the vertical axis, we're plotting kind of a metric of the complexity of the board. And so maybe this is a 2-layer board down here at the lower edge, a 2-layer board, and it's only got a few components on it, it's low density, but maybe this is a 30-layer board, or it's got BGAs on it, or it's got really high interconnect density of components on the surface, or it's got a lot of power. There's something extreme associated with the interconnect. And so when we look at the kind of applications that are out there, they're going to map somewhere around in the horizontal axis in terms of what kinds of electrical problems that might arise, and then vertically how complex that board is. And what we're going to find is that the principles that we implement, the best design practices in order to eliminate or reduce these problems, will apply whether that board is a simple board or a complex board. And so looking at simple boards that are designed to highlight a particular problem and isolate that problem, allow you to see its effect when it's pathological versus when it's done well. Those simple boards that we can use as kind of test vehicles to simulate and to measure, those simple boards and what we learn from them will apply directly to more complex boards as well. And that's kind of the motivation, the rationale of why we're going to look at simple prototypes and understand the behavior of the simple prototypes, what the problems are, their root cause, examples of good and bad design practices. We'll do that in simple boards, and and those principles and practices will apply directly to the more complicated boards. And let me just show you again a couple of examples of these problems that we're going to be dealing with when it comes to switching noise. Here's an example of a simple test board, a two-layer board that we'll be exploring later, that has some IOs that are switching. The routing is different on one side than the other, and just because of the difference in routing, just because of the difference in the layout, the physical design, there's a dramatic difference in the crosstalk on one of the quiet lines sitting here minding its own business. Exactly the same circuit, exactly the same devices that are in those circuits. The only difference is the layout, good design practices versus bad pathological design practices, and you can see a significant difference in the amount of noise on those two identical quiet lines. Here's another example of another problem. This is about rail collapse, not about the signals, but of the power distribution. And again, a very simplified view. Here's the chip that's driving. Here are the IOs that are switching. There's some connection to the rest of the power distribution path over here. And we're describing that in terms of the power supply design, the output inductance and Thevenin resistance, the interconnect inductance, and here's an inductance from the pads on the die to where the nearest decoupling capacitor is. Without that decoupling capacitor, when this device switches, we have all of these DI/DTs passing through here. When they pass through this inductance, they're going to get a voltage drop. And to minimize that voltage drop that we see over here, we want to reduce the inductance, the IOC, and that's where we add a decoupling capacitor as a local VRM, a local source of charge during that DI/DT that decouples all of this inductance in the rest of the PDN from the device. And here's an example of a measurement. This is a device that we're switching. This is the current through it. We turn on that current pretty fast. It's 100 nanoseconds of division here, so that's in about 10 nanoseconds it's turning on. And this is the voltage that we measure on the power rail of the device. With no decoupling capacitor, when that current turns on and we get the DI/DT through this inductance, this voltage here is fixed. This voltage is what drops. And look, it drops from 5 volts down to like 1 volt. Completely collapses that voltage rail if we have the inductance in the power distribution. And now we add a decoupling capacitor in a location close to the device, and look at that drop in voltage. Yeah, there's some drop. We still want to minimize it, but it's a dramatic reduction with not having that capacitor there. The location of the capacitor influences how much residual inductance we have, and some of those features contribute to the best design practices. So this is an example of another type of switching noise. It's switching because it's about the DI/DTs. It's not in the signal paths, it's in the power path. And then one last example here to illustrate this principle. Here we have two boards. Again, another example of simple boards to illustrate a pathological and a good design. It's a 4-layer board. You can't see it, but on the bottom of this board are signal lines going up to signal vias to the top surface and then going to some loads over here. And we have some drivers on the bottom. It's a 4-layer board, 2 planes in the middle. In this case, the 2 planes in the middle are connected with shorting vias between them over here. In this case, there are no shorting vias and the 2 planes are isolated. It's like a power and a ground plane, for example. And so when the signals come along here and they go across, when they transition between the top and the bottom layers, they're going to introduce noise in that cavity. That noise is going to be picked up by a victim line, whereas here, the shorting vias between the 2 planes provides a low impedance return path. There's no switching noise in the cavity, and we'll see a dramatic reduction in the noise in this victim line. And sure enough, here is the measured voltage noise on the victim line, in this case with no return vias between the 2 planes, and in this case with the return vias. And you can see a dramatic reduction in that switching noise on the poor victim line here that picks up the noise from the cavity as it passes through. And again, a lot of these details we're going to see in upcoming webinars when we explore these problems and using these sorts of test vehicles to evaluate the root cause of the problem and the benefits of different design practices. Well, this is an example of some real prototypes to illustrate the problems, how we create pathological cases, best cases, and how we measure these problems. And lastly, I want to finish up just showing you some examples of virtual prototypes that we can use to help us understand the behavior and the effects. They'll help us visualize Maxwell's equations in these structures. And the first most important principle, I think, in signal integrity is calibrating your intuition about how return current flows. This is an example of a virtual two-layer board. The orange here is a solid ground plane, and the orange trace on top is a signal line. So this is microstrip, and the microstrip takes this kind of U shape over here, and we're going to plot, we're going to calculate what is the current distribution in the return plane at different frequencies. We're going to start at 1 hertz, and at 1 hertz, we're going to send a signal in the signal and connect to the return. So we're going to send a signal and return in on this microstrip, and it's going to go all the way in there, and we're going to collect it out over on this end over here. And we're going to look at what is the calculated current distribution in that return plane at 1 hertz. And here it is. And you can see that where's the red means a lot of current density. Where's the return current in the plane going? Of course, the signal current has to flow. It's constrained by the conductor geometry, has to flow through the signal path, but the return current is not constrained. It can flow anywhere at once in that plane. And look, where does it flow? It takes the path, the shortest path, path of lowest resistance at 1 hertz. Let's continue this process. Here's a kilohertz, 10 kilohertz, 100, and a megahertz. And you see what happens at a kilohertz. The return current is taking the shortest path. At 10 kilohertz, we see the faintest hint of some of that return current flowing underneath the signal line. At 100 kilohertz, all of that return current is flowing directly under the signal line. At a megahertz, it's even more accentuated. And so we see that to calibrate our intuition, currents that are circulating that are at higher frequency than 10 kilohertz, we always assume they are flowing directly underneath the signal path. And if we want to affect the path that return currents take, we want to change the path the signal currents take. Any currents above 100 kilohertz in frequency component are all going to be taking the path directly underneath the signal path. Let's take a look at another example. And this is about the impact. Okay, if those return currents are under the signal lines, suppose we create a discontinuity, so what? What's the impact of that? How do those interconnects with the discontinuity in the return path, how do they affect this? How do they create noise? So we're going to first send a signal through one of these traces where it's a nice wide uniform plane, and we'll see how that flows. Then we're going to send it through this structure that has a gap in the return path. So here is the current distribution in the plane, and you can see it's well confined. We send a little pulse down, it's well confined, it stays localized, tiny little bit of far-end crosstalk that we can see appearing over here as the signal propagates. If you pay attention, you'll see we're getting a little bit, there it is, a little bit of far-end crosstalk that's coupling underneath the adjacent signal lines, tiniest little bit. And now let's add that discontinuity. So here's our signal, great uniform, and it hits here, and it stimulates the slot wave mode in this gap, and that slot wave mode couples current noise from the aggressor line to all of the other lines. Look how far away that noise goes. Oh my gosh, huge amount of noise because of the, in this case, discontinuity in that return path. And then finally, here's that case we looked at with the vias. Here is a 4-layer board, signal on the top. There's a signal via, the signal transitions to the bottom layer. We're looking at the current distribution in the top plane and then the bottom plane. The signal via transitions the current in the signal line from the top to the bottom. You can see that return current transitioning from the top plane to the bottom plane. How does it do that? How does that current get from one layer to the next? Well, when we look at the electric field inside the cavity, we see that it's through the electric field, that dE dt, which is displacement current. It propagates from the top plane to the bottom plane by exciting the cavity mode. It excites the electric field in that cavity, bounces all around, and any other signal vias passing through that cavity are going to pick up that noise. And that's why we saw all that crosstalk when we didn't have any return vias. And now we engineer return vias to localize that return current around the signal line. And as the signal propagates, here it is propagating. This is the current in the return plane. You can see it goes from the top plane to the bottom plane, look at this, actually going through those return vias to the bottom plane. And now we can see when we look at the electric field in that cavity, that the electric field in the cavity is dramatically reduced. Here is that signal current that's coming from the signal line. Here's the electric field. And look, all the electric field is contained within the region where those return vias are. The use of return vias dramatically reduces this problem. Well, I just gave you a whirlwind tour. This is the overture. This is just a little snippets, the overture of what you're going to hear throughout this webinar series, looking at the problems interconnects introduce, how we can understand the root cause, and how if the design has pathological features, how that can break a design, starting with switching noise. Switching noise will be the most important feature found in every design. In addition to other features, switching noise, if interconnects are not transparent, are generally always going to be present. And we saw that root cause of switching noise is that changing current through an inductance. Generally, it's going to happen in the power rails and in signals and their return paths. Well, that identification of the problem and the root cause gives us some insight into what best design practices might be. And that's where we saw a really quick example of the use of decoupling capacitors in close proximity in order to reduce the inductance that that device sees, and the use of a continuous return plane adjacent signal line to minimize the mutual inductance, minimize the coupling to adjacent traces. Understanding the details, being able to explore design trade-offs is going to be critically important, because that's how we're going to balance how much noise we end up with, at what cost and what risk, and how quickly we can achieve that. And that's really the basis of engineering, is trade-off design. Well, with that, I just want to give you a hint about our next webinar in the series. This is going to be next month, and we're going to be talking about, okay, I gave you an idea of some of the problems. So much of it is about measuring things, and the most important workhorse instrument to do the measuring is an oscilloscope. And so next week, I'm going to give you some pointers about best practices in using an oscilloscope to measure these kinds of problems, looking at signals and looking at noise. And I hope you will join us for that webinar. And with that, thank you all very much for joining us. I'm going to throw the floor open. We'll have a little time to entertain some questions. Thanks all for joining us.